Today we are going to learn about a very special topic in physics, the wave. Now this wave is not new dance sensation. No, it is a periodic something or other that, like when you throw a rock in a pond.
Hi, I'm Jeremy Clavens, and I'm sure you guys want to learn physics in an exciting way. Well, grab your goggles and strap on your oxygen tank, because in the next 2 hours, we're going to explore the concepts of heat, waves, Kepler's laws of planetary motion, and a whole lot of other good stuff.
Now we know that physics can be a rough ride at times. Well, we, the Standard Deviants, have scoured the nation for all the introductory materials you need to know, and then hired some creme de la creme physics professors to help us out. You can count on us to simplify this stuff to make it easy to learn, easy to remember, and just a little bit enjoyable. Believe it, it's our job.
As a licensed physicist, I lead a pretty full life. The fame, the money, the glory. But none of these things would be possible if I hadn't gone to class, read my textbooks, and listened to my professors. I suggest you do the same. Maybe you won't gain fame and fortune, but then again, maybe you will.
Sometimes it's easy to forget that this is a videotape. It's easy to trick yourself into thinking that this is some obscure program on a UHF station. But rest assured, this is a videotape. So,
once you get started, anytime you feel like slowing down,
speeding up,
pausing, or rewinding, feel free to do so.
On to more important matters. There are many equations in physics, but just for you, we put all the ones we talk about on the insert card that's included with this videotape. Also, since this is the Gravity-Packed World of Physics Part 2, we'll be building on the principles we learned in the Gravity-Packed World of Physics Part 1.
Once you've reviewed, we can get down to business, starting with
Part 1, Work and Energy.
Just like Starbucks and the Wayans brothers, energy is all around us. For example, we can be energized by eating energy bars, or we can have a tremendous loss of energy after running a marathon. But to understand energy, we've got to understand the concept of work. So, let's look at that now.
Section A, Work.
It's a common experience that the longer and harder we push an object along on a horizontal surface, the more tired we get. Work is the measure of the force applied times the distance moved, or the displacement. If either force or distance is zero, then no work has been done, and nothing has been accomplished.
So if this guy pushes his pet rock across the table, and the rock goes nowhere, then no work has been done. But if he pushes just a little bit harder, the rock moves and work has been done, because the object has been displaced.
That sound you hear? That's the sound of men. They're working on the chain. Gang. See, in life, work comes with a minimum wage, a lunch break, and if you're lucky, a health plan. Of course, in physics, work is all mathematical.
In physics terms, work can be described as the dot or scalar product of the vectors, force, and displacement. So work, or W, equals force, F, dot displacement, x. We learned how to compute the dot product from the Gravity-Packed World of Physics Part 1, where vector A dot vector B equals the magnitude of A times the magnitude of B times the cosine of theta.
So if theta is the angle between the two vectors, force and displacement, then work, W, equals the dot product of F and x, which equals F times x times the cosine of theta. So, from now on, this is the equation we'll use to find work.
Remember, you can find this on your insert card.
Since force is measured in newtons and displacement in meters, the unit for work is the Newton meter. This is also called the joule, a capital J, so 1 Newton meter equals 1 joule.
You know, don't think that you can go into a jewelry store trying to exchange a Newton meter for a joule, though. The white-coated men will take you away. They'll throw away the key and you will be in a world of darkness. But you know, that's a story for another time, really. Let's do a problem now. Okay, problem.
Suppose Forrest has eaten way too many chocolates, so desperately trying not to eat anymore, he pushes the box away from himself. The box moves 0.3 meters. He pushes it with a force of 200 newtons at 45 degrees. What is the amount of work he did to move the box?
Okay, we know that work equals F times X times the cosine of theta. We have the force, 200 newtons, the displacement, 0.3 meters, and the angle between Forrest's arms and the bench, which is the direction of the motion, 45 degrees. Plugging all this into our equation, we get W equals 200 newtons times 0.3 meters times the cosine of 45 degrees, which equals 42.4 Newton meters, or 42.4 joules.
So it takes 42.4 joules of work for Forrest to push that box of chocolates 3/10 of a meter.
Anyhow, all this work stuff, it's not easy. See, because when we got to move something upward, the work done is going against gravity. So to overcome this, we have to account for gravity somehow. We do this by exchanging the force in our equation with weight. That's it. That's how it's done.
Remember, weight is a vector that takes gravity into account. Since we're pushing in the opposite direction of gravity, the work done by us is the negative of the object's weight times the object's displacement, which in this case is the height that the object moves.
We learned about weight in part 1. Weight, little w, is mass times the acceleration due to gravity. Remember, the acceleration due to gravity equals negative 9.8 meters per second squared.
Since work equals the negative of weight times height, work against gravity equals the negative of negative mg times height. When we simplify, the negatives cancel out, and work against gravity equals mass times the acceleration due to gravity times height, or capital W equals mgh.
So to raise an object to a certain height, the work done is the object's mass times the acceleration due to gravity times the height raised. Now, when the object reaches a certain height, the work that can be done by the object is the change in the object's gravitational potential energy. Gravitational potential energy is represented by capital P, capital E. So, mgh equals delta PE. We can show you how this works with the help of those lovable mismatched cartoon brothers, Bumpkin Bill and Urban Tom.
In this week's episode, Bumpkin Bill goes to Urban Tom's co-op to help move in a safe. The only problem is Urban Tom lives on the top floor. Pulling that safe up is no easy trick, and once to the top, it has a lot of potential to do work if Bill lets go and it falls. This capacity to do work by falling is the safe's gravitational potential energy. But until it falls, no work is done by the safe. It's all done by Bill while Tom just looks on. So, before Bill drops it, let's use our equations to find out how heavy that safe is.
W equals mgh is our formula for the work done on an object moving vertically in either direction.
Urban Tom's co-op is 16 meters high. If it takes 9,600 joules for Bumpkin Bill to raise the safe to the top of the building, how much does the safe weigh?
The question asks us for weight, which is mass times the acceleration due to gravity. And we also know that work equals mass times the acceleration